We've been talking about Lewis structures for a while. It's time to talk about what's wrong with Lewis structures. Lewis structures have a problem in that they don't tell you the shape, or they don't give you the shape of the molecule. This looks like the OCH bond angle down here is 180 degrees, and the HCH bond angle here is 90, and the HCO bond angle here is 90. That's not legitimate. That's not the actual bond angles around this molecule. Electrons in bonds repel each other. These electrons want to be further than 90 degrees away from those, if at all possible, and these want to be further than 90 degrees from those, if at all possible, which are going to force those to be less than 180 degrees from each other. There's repulsion here, and really along here as well, but not so obvious at the 180 degree mark. So those things, those three atoms around this central point are going to spread out as much as possible and still be in a flat perspective for this particular arrangement. They have a shape that really looks like this with a 120 degree bond angle. They form 3 points of a triangle. The three atoms around the central atom form 3 points of a triangle, and we call that geometry around it trigonal planar. Any idea why it might be trigonal? Because there are 3 points. Determining molecular shape has a fancy name. It's called VSEPR theory, valence shell electron pair repulsion, VSEPR theory. So this particular molecule had 3 points, 3 atoms around a central point, trigonal planar. There are a lot of other geometries that you need to know, and unfortunately these things need to be memorized. I'm not a big fan of memorizing things, but there are a few things that you can't get through here without memorizing. There's 2 things around a central point. That's going to give you a 180 degree bond angle. We call that linear. 3 things around a central point. We've already talked about that. That's trigonal planar. What if you have 3 things around a central point and 1 thing is a lone pair? All of a sudden we call that thing bent. There's still about a 120 degree bond angle between the 2 things that remain. 4 things around a central point, tetrahedral. If 1's a lone pair, trigonal pyramidal. If 2 things are a lone pair, we call it bent. 5 things around a central point, we call it trigonal bipyramidal. This one is called sawhorse. There's not a label there. This one's called T-shape and linear. Octahedral, square pyramidal, square planar, T-shape, and linear. Yeah. So what's the deal with all of these? I like this setup because it gives you bond angles around here. And note that tetrahedral has these other varieties that are less than 109.5. This is officially 109.5. You'll see that in a lot of places. These are less than 109.5, but there's no specific bond angle given there. Trigonal bipyramidal has 2 separate bond angles because there are 5 things around that central point. I like this kind of setup because it organizes things a little bit differently to say the electron pair geometry, anytime you have 4 things around a central atom, is called tetrahedral. But that electron pair geometry gives you a specific molecular geometry depending on how many lone pairs you've got in that 4 points around a central atom setup. So I like the organization of this one, but this one is missing bond angles. This one is a little less clear organization to me, but if you like it, that's cool. But it has the bond angle, so I love that. So we'll use these combinations of charts to label given Lewis structures, that we draw. So again, this is not something you're allowed to have. This is something you unfortunately have to memorize. I know, I hate memorizing, but do it anyway. So these 3 atoms are C with 4 H's, N with 3 H's, O with 2 H's. 4 things around the central point in all of these cases because nitrogen has 1 lone pair and oxygen has 2 lone pairs. 4 things, we would say the electron pair geometry of all of these is tetrahedral. But 4 things around a central atom, no lone pairs, this is legit tetrahedral. 4 things around a central atom with 1 of them being a lone pair, this is trigonal pyramidal. 4 things around a central atom with 2 of them being a lone pair, this is bent. So this is the electron pair geometry, and this is the molecular geometry, according to that second chart I showed you. The reason I point them out here is to say they're all tetrahedral. This guy has a 109.5, this one has a 109.5 bond angle. This one has a 107.3 bond angle, slightly smaller, even though they're also tetrahedral. It is also tetrahedral. And this last one is 104.5, even though it is also tetrahedral. The lone pair is very repulsive, especially with small central atoms. Do you have to know that water has a 104.5 instead of 109.5 bond angle? No, you need to know that water, because it has lone pairs, has a less than 109.5 degree bond angle. That's all that matters to me. Yeah, okay. Something with 5 electron domains around it, we said looks like this, with that 90 and 120 bond angle, and we would call it trigonal bipyramidal. I just noticed this typo. Don't pay attention to that. It's a bipyramidal. Yep. The last one, 6 around it, looks like this. Everything is 90 degrees from each other. That's an octahedral. Know those geometry shapes. One place where we will use these geometry shapes is in the structures of oxoacids. What the heck are oxoacids? Well, let's go back and define what is an acid. Something that makes H plus when dissolved in water. HCl is an acid. When you when you have HCl just as the molecule, not dissolved in water as a gaseous thing, that's called hydrogen chloride. The name of that compound is hydrogen chloride. But when you dissolve it in water, it dissociates into H plus and Cl minus because it's a strong acid, and all of a sudden we call it hydrochloric acid. So the way you name compounds, or the way you name molecules, and the way you name molecules that are specifically acids are a little bit different. So let's remind you of the rules of how you name acids in one moment. An oxoacid is something that has hydrogen, oxygen, and another element. We have seen some of these oxoacids on our list of 6 strong acids that you remember from way back when. 3 of them are this kind of acid, and 3 of them are this kind of acid. Is that 2? HNO3 is nitric acid. H2CO3 is carbonic acid. H2SO4 is sulfuric acid. So this one is not on the list. We're going to talk about that one in a second. This one is strong. This one is strong. This one's weak. Anything that's not one of our 6 strongs is weak. It's still an oxoacid because it's one element with oxygens all around it. I'm telling you about the Lewis structures now. One element with oxygen all around it, and hydrogen is connected to the oxygen in these oxoacids. In every single case, hydrogen is connected to the oxygen. Before we get to the Lewis structures of these guys, let's remind you how to name these crazy oxoacids. ClO4 minus, ClO3 minus, ClO2 minus, 2 minus, ClO minus. There are 4 molecules, 4 polyatomic ions that are chlorine and oxygen only. And as I went down this list, I lost an oxygen each time. The name of this top one is perchlorate. And then there's chlorate. Then there's chlorite. Then there's hypochlorite. Each of them has a -1 charge. So if you talk about the acid version of these, you add enough H's for it to become neutral. So that's HClO4, HClO3, HClO2, HClO. So according to the rules, if it's a per-8, the name is peric acid. So this is perchloric acid. And this is chlorate, so this is chloric acid. This is chlorite, so this is chlorous acid. And hypochlorite makes hypochlorous acid. That's how this little chart works. This SO4 part is sulfate. So anytime it's named an 8, the acid becomes an ic acid. 8 becomes ic. So this is sulfuric acid. The H's are almost always written out front when you're talking about an oxo acid, so be aware of that. NO2 minus is NO2 minus is nitrite. Ite becomes us. So this is nitrous acid. Ite becomes us. Nitrous acid. So what do the Lewis structures of these things look like? Sulfate, that's SO4 2 minus. SO4 2 minus is 32 electrons. We've drawn SO4 2 minus Lewis structure before. If I drew it like this with all single bonds, two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Makes it look perfect. But remember, Lewis structures are not complete unless non-zero formal charges are clearly indicated. So I can go through very quickly because I've been doing this for a long time, and you can take a little bit longer time and work it out and see that this is what my charges would end up looking like. And, especially when I see a +2, I think I can probably make a better Lewis structure than a +2. So how do I make this a better Lewis structure than +2? Sulfur is in period 3 of the periodic table, which should ding alarm bells in my head to say, he can exceed his octet, and that's okay. So how about instead of lone pairs on 2 of those oxygen, we make it double bonds. So notice that I erased a lone pair and made it a double, and I erased a lone pair and I made it a double. That makes this oxygen have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12 around sulfur. My laser's not showing up on time, but 12 around sulfur. That's okay because sulfur's in the 3rd period. So now this oxygen with double bond, neutral, no charge. This oxygen with double bond, neutral, no charge. Sulfur is now neutral, and the 2 oxygens with negatives are still negative. You're not going to avoid all formal charges in here because my ion itself is a 2 minus, so you're going to have at least 2 negative charges. Yeah, okay. So if I turn this thing into sulfuric acid, that means my Lewis structure is going to have a hydrogen connected to the 2 oxygens that previously had negative charges. So here's my sulfuric acid. I almost exceeded that oxygen's octet by adding too many electrons. Here's my sulfuric acid Lewis structure. All neutral now. Those oxygens are making 2 bonds. They are totally neutral. Okay, so if we talk about the bond order of these things, the bond order of sulfate, is sulfate best represented by only this Lewis structure or more than this Lewis structure? More than this Lewis structure. Sulfate, you really have to think about, come on PowerPoint, you really have to think about the version that has the double bonds in all kinds of different places. So there are several variations of this, right? So the bond order is not single, it's not double, it's somewhere in the middle. I'm still drawing tiny representations of the structures. Here, 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 here. Just see if I can catch them all. And I think this is my last one. I think I've got them all. So if I talk about bond order, I need to look at the same bond in all 6 of my Lewis structures to determine the bond order. So that yellow highlighted bond is down in this very bottom one, a 2. So 2 plus the next one up, 2 plus the next one up 1 plus the original 1 plus the, moving to the right now, 2 plus 1. That's all the bond orders of that particular bond divided by how many total Lewis structures there are. So 4, 5, 6, 7, 8, 9 over 6 is really 3 halves or 1.5. Not 3.5, 3 halves or 1.5. So I could do it with another bond, and let's say I'm going to highlight this one in orange. This orange bond, I added up all the same, and I would get 3 halves. And if I did another bond, like this left bond, I would get 3 halves, and 3 halves, and 3 halves. So this sulfate has a bond order of 3 halves because it's best represented by multiple Lewis structures. Okay. What about sulfuric acid? Is sulfuric acid best represented by one Lewis structure or multiple Lewis structures? Are there resonance structures of this sulfate? No. Are there resonance structures of this sulfuric acid? That's what I meant. No, not equivalent resonance structures, at least. There's this molecule and really only this molecule. That's the best one. So we say that it has a bond order of 2 and 1 because an SO bond order. We should specify that. Because this one is 1, that one is a 1, but these are bond order of 2. There's not resonance to make it fractional bond orders. So if we're talking about bond lengths of these things, these are all equal. I was supposed to say equal, but my PowerPoint is being real slow today. There we go. And these are unequal. If given some lengths, some measured angstrom values, you could say the bond order of 1 is the longest, bond order of 3 halves is next, and then the bond order of 2 is last, as in the shortest, right? And before I wrap up this video and say we all done, there are 4 things around that central atom, so I would call it tetrahedral. Wow, so slow. There are 4 things around this central atom, so I would call it tetrahedral. You can talk about central atoms, but you can also talk about the bond angles around things that have more than one thing attached, like this HOS bond angle. There are 4 things, so it's tetrahedral, but its bent is the specific molecular geometry around that oxygen. The bond angles of all of these things should be approximately 109.5. The HOS bond angle, the OSO bond angle, all of them are around 109.5. All right, put a pin in it. We done.